Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We were discussing flow facilities for compressible flows. The only other flow facility which we need to talk about is low density facility. Of course, does it really fit into compressible flows? In a way, yes and no, because if you think about when I am launching a rocket, then the flow in the front of it is actually a compressible flow, because the rocket will slowly accelerate all the way up to Mach 20 or so. If it is going all the way up that very high speeds, then maybe the flow in the front will be forming the same kind of shocks which we are seeing in regular compressible flows. But there may be a situation where when it is reaching Mach 20, it may be up in altitude so high that it is not in continuum anymore. If it is not in continuum, you are going to have different physics. It is not going to be the same. Okay, it will not exactly behave the same way. Shock will not be very thin. Shock will start becoming a big region instead of one thin line. That also starts happening in non-continuum situations. Okay, when I go to more and more rarefied conditions, we will have to worry about that. Okay. If I look at when should I worry about it, I already talked about it on the very first day, I believe. Knudsen number, the mean free path of molecules in the gas, divided by the dimension of interest to us. Typically, if I think about a rocket, then the diameter of the rocket is what we will use for that kind of dimension. If this number is more than 0.01, then we cannot say that continuum is valid exactly. Okay, you will start having more and more errors if we use continuum to study the flow fields of this type. Okay. When will this happen? If this number is going to become bigger, that means my diameter is getting smaller and smaller compared to the mean free path, or mean free path is becoming larger and larger compared to my size. Okay. If I am interested in 1 meter diameter rocket, then the size is going to be of the order of 1 centimeter, mean free path is of the order of 1 centimeter, then things will start affecting. Typically, mean free paths are going to be of the order of less than 1 micron or even nanometer probably at higher pressures and temperatures. But when we are going very low density conditions, then things will become non-continuum situations. Okay. So, if I think about density at 50 kilometer, this is roughly 10 power minus 3 kg per meter cube. Okay. While of course you know density at sea level, 0 altitude, is 1.2256, you should remember that, kg per meter cube. Now if it is 80 kilometers, then it is going to be 6.5 into 10 power minus 6 kg per meter cube. If you think about it, we were having order of 1 kg per meter cube at sea level. I did not write that number here, 1.22 of the order of 1. It became 1 by 1000th of that density by the time we went 50 kilometer altitude. Okay. And from here it went of the order of another 1 by 1000, not exactly 1000, slightly less than 1000, 1 by 300 or so. Okay. So 1 by 200 kind of order, again further down. Okay. If you think about it, people start using different units. Torr is the unit for pressure there. They will start using torr for unit of pressure, which is 1 torr is 1 millimeter of mercury. The pressure exerted by 1 millimeter of mercury, that is 1 torr, and typically this will correspond to of the order of 10 power minus 3 torr. Okay. That is the kind of numbers we are talking about. Okay. I am talking about 1 micron of mercury height is the pressure actually exerted at that 80 kilometer altitude conditions. Okay. So now if we want to do this kind of experiments at our sea level or ground level conditions, we have to create a setup where I can provide the conditions corresponding to 80 kilometer altitude and the corresponding velocities, temperatures, etc. Okay. So to do that, what we do is basically do the experiment in a vacuum tank. That is the simple way to put it. What we will have will be a big tank, and I am going to connect it to vacuum pumps, several pumps, and depending on the vacuum I will run all the pumps, or some of the pumps will not be used sometimes depending on the vacuum condition. I will just be evacuating one chamber, and remember that since we have doors etc. on this, there will always be a little leak, and little leak matters a lot for very low pressure conditions. So the leak should be arrested very well. That is one primary problem with them. Other than that, the pump should be continuously running to maintain the pressure, because there is always leak, and the pump should be removing the excess molecules that are entering due to leak. Then the pressure will be maintained. That is the idea there. And the pump should be running for that, capable of running with the required leak rate. That is the idea. Now if I want to have a flow in this condition, if I am thinking about flow over say my GSLV rocket front nose cone alone, I want to study flow over it, and I want to think about Mach number say 15, then I need to create a pressure difference within that conditions. Okay. So I will split this chamber into two parts. I will call this my stagnation chamber and this my other side. Okay, this is the back pressure, the vacuum chamber. What I will do is I will put a nozzle inside here, which is designed to give whatever Mach number we have talked about. Typically if we keep such a situation and this pressure being extremely low, I can create a big jet like this. Of course, you know what happens, there will be a barrel shock and a Mach disk etc., all that will happen here, but that is not our interest currently. We are interested in putting our model somewhere in here. We said GSLV nose cone in here, we are going to put that model in here, and then we are going to study what is the flow field around it, maybe a shock is formed etc. And if we design the nozzle well, I will get uniform Mach number for this whole length. Okay. And then now I can study the flow around it. Typically in our lab here, rarefied gas dynamics tunnel, we will use temperature measurements in the front, on the sides etc. to find the heat transfer rates for this. Okay. That is one way of using this facility. Of course, you can think about shock patterns and how to think about interaction of this with the other side pod sitting here. Will it go and interact with that shock, and will that cause any trouble? That kind of things can also be studied with this. Okay. If I keep a particular P naught such that I want a particular static pressure in front of the model, then my back pressure should be much lower than that, and also to maintain the back pressure very low, I have to now think about this P naught times this throat area mass flow rate, right. That should be able to be pumped by these pumps sitting there, vacuum pumps. All that should be able to be handled for this to be working in the steady conditions. Okay. Now if I set P naught as this and T naught as room temperature, then for Mach 15 if I think about, that is going to be very low temperature, extremely low temperatures. Okay. And that is again not good for us. We want to study exactly as if it is in space, whatever is the temperature there, maybe of the order of 100 Kelvin, 150 Kelvin somewhere. So to get that temperature, I have to now create hot T naught here. What people do is just have some kind of electrical heater inside here, so that the low pressure gas here is getting hot as it is going through this. Okay, and somebody should be monitoring it, so we will put a temperature probe there in front of it, so that the flow is going to go through this. This is the design, so that now I can set a particular T naught, the stagnation temperature and stagnation pressure, so that I will get the required static pressure T and static temperature and pressure there, and for that particular Mach number as designed by my nozzle. This is a reasonable design which people use for this. Okay. Of course, I can now talk about what are the probes used to measure pressure etc., but I think that is slightly beyond the scope of this course, so we will not talk about it. There is a special probe to be used for finding stagnation pressure in low density facilities. We will not talk about it in this particular course. Okay. But that is the idea for low density facilities. Okay. Now we will go into, we have already talked about a lot of flow facilities. We will think about how to measure pressures in compressible flow experiments. If I think about compressible flows, I can think about supersonic and subsonic and split them separately. If I first talk about only the subsonic cases, subsonic, if I want to find velocity, if it is very low subsonic, that is incompressible world, we will just use stagnation pressure and static pressure, and that is going to give me, based on our Bernoulli's half rho u square, I am going to get the velocity if I know the density. That is what we will do. But if it is compressible flow, we already saw the connection between this and the other expression we had from compressible flows. We had the connection between this and this. This simplifies to this for very low Mach numbers. We already did that. Okay. So what we do if it is subsonic compressible is just go look at this, and from here I am going to get a Mach number if I know the gas. That is, I should know gamma for that gas. Okay. This is the basic idea. If it is subsonic, if it is supersonic, we will come back to it. Most likely, I am going to use the same formula anyway, but we will come back to it afterwards. How will I measure stagnation pressure? Stagnation pressure is simple enough. It is just going to be a tube that is facing the flow, and on the other end, it is not letting a flow through continuously. Okay, there is going to be some pressure measurement device here, say a manometer. If I use a manometer, that is going to stop the flow from going. It is not going to be a continuous mass flow rate, it is going to go and stop somewhere. Okay. So I am taking a flow here and it is going and stopping there. In that situation where I am saying that the velocity that is coming here with whatever is the free stream velocity in here is slowly going in, and by the time it reaches the other end, it is going to be brought to rest, because I am thinking about steady state measurements. It is going to come back to rest. So this particular device is called a pitot probe. Okay, this is used in subsonic a lot of times. Even in supersonic we can use it. There will just be a small change, we will come back to it, but I first want to talk about all the probes in subsonic conditions, then we will go to all the probes in supersonic conditions. Okay. Now if I want to measure pressure, static pressure, if it is on the wall, what is the definition of static pressure? It is as if I am moving along with the fluid element and measuring the pressure. Okay, that is, the fluid element is not really pushing on me. That is the idea. If I have a side hole this way on the wall and the flow is going like this, the fluid element is not really pushing on me as long as this pressure is same as this pressure. Okay. Then I can say that the streamlines do not want to bend this way. When will it bend this way? If I have a through hole here and the pressure here is higher than this pressure, then there is a through hole, there is going to be a flow this way. We do not want to have that situation. Again the same thing as here, if I put a pressure device there, say a pressure transducer, then that is going to be sitting somewhere here, that will stop the flow, but this system will come to equilibrium when this pressure is same as this pressure, and after that the streamlines will just be going straight. Okay. That is what will happen here. If this is the case, then I am actually measuring the pressure at this location, at that entry of the port, and then at that point I am going to say I am measuring pressure in that particular pressure port, and it is going to give you the static value. Why? It is not pushing anymore on the sides, it is not turning into the flow. Okay. This is the typical method. This is the wall tapping. Okay, I am tapping from the wall to measure the pressure. Okay. If I think about I want to measure somewhere inside my flow system, say I have a full test section with m less than 1, let us say, and I want to measure static pressure somewhere in the middle of the test section, then I need to create a local condition like this. I have to create a system where there is a wall and a side hole from there. How will we do it? We will have a tube, we will have a probe that is like this, where it is just a straight tube with some nice smooth ending in the front, and then we will have a hole on the side. Okay, typically there will be 4 holes, top, bottom, front and back. There will be 4 holes on the sides. So now it is going to average around all the sides of this tube, and I will get a net 1 value pressure here, and that is going to be taken out through this to some pressure measurement device, most likely some pressure transducer or a manometer. Okay. This is a device which people use. What am I doing really? It's the same as whatever I have done here. It is just flow is going to go parallel to this, and I am looking at pressure measured perpendicular to the streamline. That is all I am doing here. This is going to give me again static pressure value. Okay. Now, what are the considerations I have to have? What if I have a probe that is very short from the front to the hole? Let us say a hole center to the front, typical numbers people use are 3 to 8 times the diameter of this. If this is my D, then this is going to be 3 to 8 D, 3 to 8, okay, not 3.8. Okay. And the other distance, the holder to the hole position of the order of 8D to 20D, 8 to 20 times the diameter of this tube, that is what we will use there. Okay. Why do we have to worry about this? What if it is less than 1D? What will happen? Then if I look at zoom into that region, if it is less than 1D, then my holes are here, then the flow streamlines are just now turning. They are still accelerating, which means the velocity is not same as what it should have been without this probe. I have changed the free stream velocity to something higher here. I do not want that, I want to measure without disturbing too much that particular flow field. So, I have to think about going far away from here. If I go far away from here, it is going to become parallel. But still, if you think about it, this probe is blocking some area in my whole test section. Ideally, if I think about it, the area available for the flow has decreased. What we have to do is minimize this so that I am not intrusive. As much as possible, we have to make the D as small as possible. If I make the D small, the hole size, I have not marked the hole size. The hole size is 1/10 of D, typically they use. We will come back to that why next. Okay. But if I make this D small, then I have to drill extremely tiny hole and it has to be accurately placed. That is going to become a trouble. Making small holes less than 0.5 mm is very difficult. Okay. Of course, now we have laser machining, it is getting easier, but it is still difficult, it is not very easy to do all the time. Okay. So, that kind of precision machining is needed for that if you want good measurements. Okay. Why do I have to worry about this length from here to here? Now I have to think about this bottom flow going and stopping in front of it. I am going to create a stagnation point in front of this, which means pressure from here is, this is subsonic flow, right. So, pressure from here is going to increase immediately from here till it reaches there, so that the flow is adjusted by the time it reaches there. Right. Subsonic flow typically does that, it adjusts to the incoming flow. So, it will start adjusting from here itself. So, I will get wrong reading unless it is so far out. Typically people keep it more than 10D, okay, so that things are not interfering there. Okay. These are two things. Now, I will talk about this 1/10D. Why should it be 1/10D? What if it is just 1D? It is easier to think about in this particular situation. Yeah, I have a picture here. Imagine that is the same picture. I will just draw that picture exactly, that probe. This is a tube with a hole, and this is where my flow field is. And I am thinking about this situation. I am going to say, if the hole is really big, then flow will start doing this. Flow will start bending in and coming out. If the flow has a small component into the tube, then I am going to measure slightly higher velocity than the higher pressure than the static pressure, because this velocity going in has to stop this way and then come back accelerating this way. Okay. So, I am going to get a higher pressure here. Another way of looking at it, the streamline is curved this way, meaning there will be a centrifugal force this way, that is going to give a extra pressure gradient this way. Okay. So, that is again pushing. So, I am going to measure something more than static pressure. But if I decrease this hole size to something much smaller, then the amount of curvature you are going to have is extremely small, that I can neglect that pressure change and I will get as good a reading as possible. Ideally, this hole should be as tiny as possible. Okay. If it is too tiny, then there is a possibility of dust coming and blocking it. That is the other extreme problem you will start getting into. Okay. But we have to think about this size also. Typically they talk about the hole diameter of the order of 1/5 of boundary layer thickness. Okay, 1/5 of the boundary layer thickness is what they typically talk about. If I think about static pressure holes, typically if my setup is small enough, we will think about something between 0.25 millimeter to 2.5 millimeter. Even if it is one big room size of wind tunnel I have, I will still use only 2.5 mm maximum size for the port typically. Okay. These are the typical numbers people use only inside this. Okay. This is for static pressure, wall pressure measurement. Now if I want to measure velocity with just one probe, what we do is use static and stagnation pressure together. I will just give you a very complicated probe. It is going to be a static probe with a P dot probe inside it. Okay, that is the idea. It is going to be there will be holes on front, back, top, down, and they are all going to open up into this annular region. Okay, and the center pipe alone is going to go separately. If you look at without this front hole, it is actually whatever probe we already drew for static pressure measurement. Along with that, I have this extra centerline hole for a P dot pressure measurement. Now I will have to take it, of course, to two separate pressure measurement devices. This is going to go for static pressure, this is going to go for stagnation pressure measurement, and from these two now I can go and get my actual Mach number or pressure depending on whether it is compressible or incompressible. I can get to that particular situation from here. Okay. This is the probe people use, and of course now I can think about a modification to this. Instead of having it this far out, I will just draw the front portion of it in isometric view. There is a center hole and then there is 4 holes around it. Okay. So imagine a sphere, hemisphere in front of a cylindrical thing, and you are having 5 different holes. And of course in this particular thing, each hole is separately connected to individual tubes going out all the way, and so you are going to have 5 different pressure measurement devices which are going to give you individual pressure readings here. This probe can measure the angle of attack of the flow with respect to the probe also. If I send a flow like this is going to measure close to stagnation, and that is going to measure much lesser. Differential between these two will give me my pitch angle. Differential from this side versus from that side will give me yaw angle like from these two. Okay. And if it is going straight in front, then I can use these values with the center value to get a velocity, but that has to be calibrated. It is not going to be same value as the top this probe, because it is not going to give you static pressures on these 4 probes. They are going to give something between static and stagnation, and that has to be calibrated. Okay. This all this time we have been talking about just simple measurement of velocity and pressure, and this is all used typically in subsonic situations. When it goes supersonic, the primary change is if I introduce anything in the flow, there is going to be shock in front of it. Okay. So if I think about putting a stagnation probe, if I put a stagnation probe, then there will be a shock in front of it. If there is a shock in front of it, then I will get, if you think about it, it is going to be a bow shock. Okay. And why will it be a bow shock? Because it is like a bluff body, it is stopping completely. Okay. It is like, even if I put a body like this in my flow, it is going to form a bow shock like this, and the centerline region in front of it is always going to be a normal shock. That is what will happen here also. It will form a normal shock at the free stream Mach number m1, and of course you should know that P01 is the original P0, which is what we want to measure, but we will get only P02 because it is measuring only the post shock subsonic region P dot pressure. It will give me only P02. So now it tells me that in this particular condition I need one more extra information to get my Mach number out of this. So I am going back and saying I need P01. Typically what they do is they know their wind tunnel settling chamber P01. They are going to set it because when they want to run the facility they want to measure it somewhere. They will typically measure it in settling chamber P01. They will use that value here and P02 here. Now you just go and look at P02 by P01 in normal shock tables. Normal shock tables for that particular gamma value for the gas. Then from there you can back out Mach number. Okay, that is the way they measure it. Once they know Mach number, of course they can now tell what is the static pressure here or static temperature if I know stagnation temperature. Okay, all the information you can get out of this from here. Okay, this is one simple probe. If I really want to measure the static pressure somewhere, okay, then they use a long cone probe. They use a long cone probe. In supersonic typically things will be very sharp. Why? That avoids bow shocks. If it is very sharp and the angle low enough, it will avoid bow shock, it will be an attached oblique shock. So this particular situation they are going to form a cone and then some tube of diameter d, okay, and typically they will have a hole somewhere far away from this cone end and typical distance 5d and this one 15d, okay, where d is the diameter of this tube, okay, 5 times the diameter, 15 times the diameter, etc. And typical this basically 15 by 1 gives you the diameter to this cone angle of the order of theta is half angle of the order of 5 degrees. And sometimes if you are constrained with the length, then they can go as much as max theta of the order of 8 degrees. More than that this probe cannot be used. Okay, this basically is a very long probe. Okay. Now if I look at what is the hole size here, can be anywhere between 1/10 to, I will put in between 1/10 to 1/4 d, okay, 1/4 d. Typically if you are using smaller is better than bigger. When it is bigger you are going to have slight problems of streamlines bending into it and out of it. And of course you should know that they are going to have holes on the top and bottom, front and back, 4 holes to average around all the 4 sides. And this tube is going to go to your pressure measurement device and that is your final static pressure device you are going to get. How does it work? Why does this work? This is also going to form a shock. If it forms a shock, I am going to have P2 immediately after that. But think about it, the angle is very, very low, which means if I think about my theta beta m curve for any Mach number, it is going to be some curve like this. This point is 90 degrees of course, and we are going to say it is weak shock, and theta is only 5 degrees. Okay. If this is the case, now beta can be whatever angle, but it is very close to Mach angle, okay, depending on the Mach number. If I have some other lower Mach number, it is going to be somewhere here. It is very close to Mach angle, which means it is a very, very weak compression wave. If it is a weak compression wave, the P2 by P1 is almost 1, okay, it is close to 1. That is the first thing. So I am going to have a shock here. It is slightly stronger than a Mach wave, and the flow coming here is going to turn along the cone like this, and after that it sees a expansion. So it is going to have an expansion wave here which turns it back to this. Now this expansion is also turning by the same angle, 5 degrees. It went up by 5 degrees, it is coming back by 5 degrees. This 5 degrees change will roughly negate the increase in pressure in this wave. That is the idea of this probe, okay, and this approximation that this expansion will negate the compression will go invalid as the theta increases. When the theta increases, then this shock is much stronger than the expansion. This is isentropic and this is non-isentropic, so there will be more losses here, okay. So that is the main idea you have to think about. The probe works because I am going to say that the shock is increasing pressure, but the expansion is going to decrease it back to the original value, and I am going to measure it here. This is the idea of these probes, okay. That is the way it works. So actually I will show you the probes. So this is the long cone probe we are talking about. You can see the cone portion is only up to here, and after that it's a straight tube, and this is the portion where we are going to do the measurement. And you can see one of the holes here, there are 4 such holes on all the other sides. Here you can see this arrow which is showing that hole in detail, and if you see the next one, we can show actually much closer 2 holes sitting in there, and inside this tube goes all the way into this, and then it becomes a bigger tube diameter, and that goes to our measurement device. The actual shock wave formed from here will be a very weak shock wave, and after that you are going to have a slightly higher pressure coming here, static pressure, and then there will be an expansion at this point because the flow is again turning back to parallel to this tube. So that expansion will roughly bring it back to the original free stream pressure along this tube, and that is what we are measuring using this. That is the idea of using this long cone probe. This is the other probe, the pitot pressure. So this is just a straight hole. Since we want to measure the same probe volume, we want to put same diameter tube as the static, and then we will say that the actual measurement is of this size resolution, and then this tube is just going straight into the other tube, and then the tube size becomes bigger for easy handling of pressures, and this is just going to measure stagnation pressure. In case if it is a supersonic flow, there will be a shock in front of it, and we will get only P02 value from here. If I want to measure using some other probes, say I form a wedge in my supersonic flow, okay, I am putting a wedge in my supersonic flow, and I am going to put holes on the side of the wedge, and then I am taking 2 pressure data out. How do I store this? If I look at a 3D isometric view of this wedge, what we typically do is we will have a tube which is going to take the hole from here and take it through this way. There will be 2 tubes running inside one bigger tube, and that whole big tube is your holder for this wedge. I am going to put it inside my flow, measure it. The flow is going to be this way, and I am going to put it inside and measure it. Okay. If I put this probe inside and I have flow coming like this, okay, what will I get? I know the original angle of this wedge, and if I get some pressure here, if I already know static pressure here and I get a static pressure here, P2 by P1 will give me my shock, and that will give me my mark because I know this angle theta. I know my deflection. If I know my P2 by P1, I can back calculate my M1. That can also be done from here. This probe also has a speciality of giving us the angle of attack for the flow. If my flow is not going straight along the wedge axis, but is going slightly this way, then I will get individual values that are different from top and bottom. I can use that to give you the pitch angle of the flow. Okay. Typically people use this in aircrafts. When they are flying an aircraft for the very first time, they want to have all kinds of probes on it. This will be one of the probes sitting there on it. When they are testing what is the actual flow field around it and they are measuring it, they will use this kind of probes also. Okay. And a better version of this is to get a pitch angle and yaw angle. Okay, you know, pitch is looking going up and down and yaw is turning sideways left right. The next better probe will be, I will try and give you the front view first. Imagine something like this. There is a hole, something like this. Now I will tell you what it looks from the side. This is what it looks from the side. If I see, it is going to be a straight flat portion in the front which is going to get measure a P0 value. Of course, remember if it is supersonic, it is going to have everything behind the shock only. So it has to be calibrated for conditions, and then I am going to have these side holes. If they both the top and bottom are giving the same value, then I am not having any pitch angle. Pitch angle is 0. If top is giving more than the bottom, I am having flow coming downward. Okay. So like that, I can now think about left right also same thing. The picture looks the same even if I look from this way. This side view and other top view both will look similar to this one. Okay. That is the kind of probe you are going to have. It is actually having a wedge like shape this way and wedge like shape this way, and the front portion cut off. Say this is a 5 hole probe people do not use it much. It is called a yaw pitch probe or pitch yaw probe. Okay. I haven't seen so many papers using this now. Okay. Nowadays people just put pressure tappings on the model and just live with it. This is probably just to calibrate your wind tunnel or so. After that I do not think they use it. Now if I think about what kind of problems will I have in measuring pressures using these probes, the first thing I have to think about is what should be the hole diameter. You know that if the hole diameter is too big I am going to get wrong reading. If it is too small, is it going to be any problem? Can I make a 1 micron hole? Machining is a problem. Let us say I have micro machining devices. Will there be a problem? What will be the problem? Response will be really small. Why? Now I have to think about, I have a very small hole in a wall and I am going to take it to some pressure measurement device somewhere there, say a manometer or something sitting there. Now if it is a very tiny hole, then when there is a pressure change here, suddenly static pressure increased, let us say, then what will happen? This small hole will now restrict the flow from going this way. Initially, since the pressure is higher here and it is not same as this pressure inside here will rise. How will it rise? Flow will go through this to increase this. Now flow going through this is resisted by this very small hole, and because of that the flow takes a long time to go through this to fill this whole section. Only after this whole section is filled with that new pressure, it will start giving correct reading here. So that is going to be a problem. How will I avoid this problem? I will put my pressure transducer directly here. This itself is my pressure transducer. If I use a piezoelectric or piezoresistive transducer, I will directly put it there at the wall, and that will be a diaphragm deflection based gauge. So if the diaphragm deflects this way, that immediately gives me signal. That will avoid this transit lag. Okay. This is actually not just a transit lag, it is also going to have a response problem. Because it is a tiny hole, there will be a response problem. If I have long enough tubes, then long tubes will have transit lag. If I am taking this going 100 meters and then only measuring things, then I am going to have, when there is a change in pressure, that effect has to go all the way through there before it starts measuring. That will take its own time. How much time will it be? The minimum time will be speed of sound and the length based time calculated. Okay, length divided by speed of sound will be the minimum time before this will start sensing it. That itself will have a pure delay. Okay. On top of that, you are going to have response delay because it is a very long system and I have to fill this whole tube with new pressure. Then only I will get the final pressure here to be correct. Okay. So that will also have some response. Ideally, we should want to decrease the volume inside these leading tubes. So it should be very thin tube as much as possible. Nobody will use a 5 mm ID tube for this. People will use 1 mm or half mm ID tubes for this. That is easier to use. Simple, response will be better. That is the idea. Okay, so there is a limitation on how small or how big I can go with the diameter of the tubes. Okay. Now the next thing is, if the flow is going changing pressure, oscillating pressures. The pressure is oscillating up and down, up and down. If it is oscillating too fast, then before it responds itself, the pressure has started coming down. Then I am having a bandwidth limitation based on this length. Those problems are gone if I use a pressure transducer directly at the wall. Okay. Now by the time I start filling this, the pressure decreases. Then what will happen? I will measure only half the pressure rise. Okay. That kind of problems will start happening. We want to avoid all that. We want to put pressure transducer directly at the wall. That may not be always possible. If you want to put at the wall and the model is very small, you may not get a transducer that is small enough to be put at the wall on the model. That may also happen. Now typically I talked about P naught and static pressure measurements for finding velocity or Mach number. If I want to directly measure velocity or Mach number without using pressures, this is actually inferred value, right? Instead I want to use directly the value, then the easiest thing to do in supersonic flows is to, if I put a, let us say I will put a wedge, this is my supersonic flow, and I will put a wedge and I want to see the flow field, all I have to do is put a very thin cellophane tape on top of my wedge. Let us say my wedge size is of the order of 15 mm. I will put a very thin cellophane tape on top of it. The flow sees it as a very small bump. What will it do? Locally, if I zoom into it, it looks like this, and immediately after that it goes down like this. This is what it looks like locally. So the flow sees it as a shock followed by expansion. It's a very small change, but it is going to do this. So there will be a shock and then expansion, they will both cancel each other, and finally there will be only a Mach wave. Okay. It's not exactly a Mach wave, it's probably slightly a compression wave or slightly an expansion wave. Most likely in this point it's a slightly compression wave, and in this point it will be a slightly expansion wave. You will see that, but since it is almost Mach wave, I will get lines that are having angle with respect to the flow exactly mu, and that I can now use to find Mach number. That is another way to find Mach number. Okay. But this will work only if it is supersonic. If that region is subsonic flow, I will not see Mach numbers there, Mach waves there, and so I cannot find Mach number that way. Typically they use this method in nozzle flows. If I want to look at my nozzle, typically I will show you a picture of this some other time, maybe in 2 classes. If I have a nozzle like this and I want to find the Mach number in this region, what we have to do is put these cellophane tapes all along this way, or some small bumps in the nozzle all along this way. What will happen? Because of that, it is going to send out waves everywhere. Each of them is going to give you one set of Mach waves, and they are just going to go straight through. Same thing will happen from the other side also. Now you are going to get a full grid of Mach waves. Now if this grid is all exactly looking like parallel lines crossing each other, then I am having very uniform flow. If the grid is not always having the same Mach angle, that it is changing from point to point, then the situation is such that locally it is going to have that Mach number, at some other point it is having some other Mach number. That means this point angle is lesser, means higher Mach number. Okay, like that it will start becoming. So now with this full grid, I can now tell exactly what is the Mach number at every location. Also I can tell the flow angle, because now I have 2 Mach waves. If I have Mach waves going like this, then I know the angle bisector between this will be my flow velocity direction. That also can be told from here. Okay, just all this is coming from flow visualization. Simple enough experiment to do. I will tell you how to visualize the flow, that is my next class mainly. Okay. Other than this, if I want to measure velocity directly, people can use something like a hot wire. It may not work very well because the wire is so feeble, it will just break. Okay. Nobody uses hot wire in supersonic flows. Okay. It is too fast and it cannot withstand, the wire is too thin to withstand these forces. But people can use laser Doppler velocimeter. I do not want to go into that, that is a big problem by itself, that will take one more class, I do not want to do that. Okay. So people can use LDV for measuring this, LDV or LDA, whatever they call it, they can use that also. Okay. Now the only thing left is experiments. When you are trying to design an experiment, what should you think about? After that we will stop. Okay. I already talked about it a little bit when we were discussing transonic flows, transonic tunnels, but I will anyway formally represent it here. If I think about a particular test section I have and I want to put a model inside that, we know the model shape, right? We know what we want to put in and study, and I know my Mach number for my facility. If this is the case, now I have to think about, first thing, whether this is actually blocking too much area, that is model frontal area, not the surface area. Model frontal area should be less than A2 star minus A1 star. You guys know these A2 star and A1 star for the tunnel, right? Even if the tunnel does not have a A2 star, you will calculate an A2 star as if the tunnel should be having one, and then check whether this is matching. If this number is less than that, then there is no problem. Okay. yeah, if it is less than that, then there is no problem. If this number is more than this, then what happens is this portion forms a nozzle second throat. This point will get choked, okay, and your flow will be different now suddenly. And it so happens that if it is more than this value, then this portion is less than the A2 star, which means my tunnel itself gets unstarted. The whole tunnel gets unstarted and the starting shock sits somewhere here, it never crosses. I will show you actually videos of this also, show a starting shock never going through. I have a video of that also in Schlieren. I will come back to that maybe 2 classes from now or so. Okay. The other thing we need to think about, if there is a wedge or some body in the flow, I have to think about the shocks from here going and interacting with the wall. If the shock from here is going and interacting with the wall and coming back and hitting the model, that is a problem. We should not be using that design. But if it is going more like this, then it is good, then there is no problem. Okay. So this is related to the size of the model. If I decrease the size of the model, then that problem will length along the axis. If I decrease that, then this reflected shock will not interact with it, then it is better for us. Okay. That is the way we have to think about this. Now the only other thing about the model holder is this. When I think about this holder here, when I think about the cross section area, it is not just this frontal area, I have to put plus holder. Holder cross section frontal area also matters. Everything together should not be more than this. But if I put it behind, then at this location model area can be lesser. Behind the model I can have a thinner tube holding the model. Why do I say tube? If it is a tube, now I can have some information from here transported through this, say a wire going through the tube, or actually a pressure port tube, pressure tube can also be going through it. Okay. Any of those can be taken in through this. Typically people use a tube, and typically the cross section for this is again a sharp edged thing. They will typically use something like this with the center hole, so that I can transport wires through this. This is a cross section. If I cut it like this and see from the top, it looks something like this, okay, where this is the actual material present and it is a hole in the center. Now this is going to take the aerodynamic loads and I am going to form only oblique shocks here. That is again beautiful, okay, right, we are not losing lot of P naught. Okay. And finally I am going to have hole through this, and I have to design it such that it should be able to withstand the aerodynamic load on the model. If you make a mistake, the model will be broken at this corner and the whole probe and holder and the model will fly through. Typically happens in experiments once in a while. If your test section is very long, then I will have to talk about, if my nozzle ends somewhere here and my test section is very long, now I have to talk about friction. Okay. Now because of friction I may be losing P naught continuously and my Mach number will go towards m equal to 1. We have a tunnel for Mach 4. If we have parallel plates here, then Mach number is 4 around here, and 20 centimeters inside it is 3.5, and 20 more centimeters inside is 2.9. That is what you will get. Okay. But to compensate for this, what do? We already discussed this in fan of flow. If we are having constant area and Mach number is going towards m equal to 1, we will go expanding area, we will make this diverge a little bit, so that the expanding area is going to increase the Mach number while the friction is decreasing the Mach number. So overall effect will be constant Mach number everywhere. So I will have 4, 4, 4, 4 everywhere. Okay, that will happen only for one particular divergence angle, that is related to the friction coefficient F for that particular surface and the Mach number there. 4 FL by D and the Mach number relation needs to be used to calculate this. Okay. So that is one more thing you need to think about. I think after this we will go into flow visualization, which will start next class. Any question? Will the diverging be linear? That is easy for experimentalists to do, so they will keep it linear because that is one big plate. I will just shift the whole plate hinged about this corner. That is easier to do, so people will do this. Of course, I have seen some facilities where it is going through 2 deflections also, but mostly it will just be one straight line thing. That is nice, that is easier to do. As the Mach number goes closer to 1, the change will be more, but if I am trying to maintain constant Mach number, all I need to do is one particular angle, that is enough. If I want variation in Mach number in a particular way, then I have to have this thing curved to some particular manner, otherwise we will ignore that. Okay. Any other questions? Okay, so we will go start with flow visualization next class. See you people next class.